I'll be talking about all the history that have gone on in building this collider, the minds that have gone in even before the construction of this collider started, and then the building phase of this collider, the detectors, and then finding the Higgs boson, the discovery phase of the Higgs boson, and then what are we doing now and what will come next. So the talk is corely titled on Unraveling the Higgs boson at the Large Hadron Collider. And this is taking place at CERN, the European Center, the Organization for Nuclear Research. It's one of the world's biggest laboratories, so it's in fact the largest laboratory of the world. And you can see this, so this is Geneva, and it's lying on the France-Switzerland border. And here is the Large Hadron Collider ring. So this is where the proton beams are accelerated and then they collide with each other. This is a 27-kilometer long ring. So this is basically the distance between Indian Institute of Science and the Bangalore airport. So it's so long. And here you can see the Geneva airport, in fact. So at CERN lies the world's fastest and the most brutal racetrack. So this is basically not racing with scooters or motorbikes, but in fact racing with protons around this 27-kilometer circuit at almost nearly the speed of light, 99.999999% of the speed of light, crashing head-on into each other almost 40 million times a second, these bunches of protons. So basically the protons come in bunches, so one bunch of proton coming with another bunch of proton, and then it goes into each other, smashes into each other 40 million times a second. Doesn't mean that the protons, each of those individual protons all smash into each other. This I will come later, but that doesn't happen actually. But okay, the core idea is it almost goes at the speed of light, nearly the speed but less than the speed of light, of course, and then crashes into each other in the emptiest space in our solar system. And so the beam pipe where the protons are actually colliding with each other is evacuated to the same vacuum as interplanetary space. The pressure is about 1/10 of the surface of the moon. So, and this is the beam pipe. So basically you just heard about the magnets and how it's guided. The beam is guided in the previous talk, and it's in one of the coldest regions of the universe. So basically these magnets are cooled with this liquid helium, maintained just at a couple of degrees above absolute zero. So that's around 1.9 Kelvin. This is a little colder than the interstellar space. And this is to be watched, so these collisions that happen is to be watched by some of the most complex eyes that we have ever built. It's really like a camera. So we are, so what's happening here? It's getting cut off. So this camera is watching at 40 million times a second this collision events. So this is what we call the most complex eyes. So the most complex eye is basically the detector that is surrounding this beam pipe. And so around the collision point where the collision is happening, so you have this 27-kilometer long tunnel, this ring, and so two bunches of protons, say, meet at a point where the collision happens, and around that point is our detector, which we call the most complex eyes that we have ever built. And that detects all the particles that is coming out of that collision. And then what do we get? We get data. the collision data. And that is to be analyzed by the most powerful computing system in the world. So all these events that come out of the collision, so our data, we have to, and it's huge in size. And the detectors will spew out analyzed data at 700 megabytes per second. That is like 30,000 encyclopedia every second. And that's 15 picobytes per year, so 20 kilometers stack of average CDs per year. So in 1 year, say in 2011, the amount of data we collected, if we just stack in CDs, it's like 1.5 times Mount Everest. So you can understand, but why are we doing all these things? We are achieving like the most complex things and going into the most complex things, but why? The aim of particle physics, to achieve this aim of particle physics, like what's everything made of and what holds everything together. So basically our fundamental understanding of the universe, this is what we are going for. And what's everything made of? Basically the matter particles, our universe, the rivers, valleys, trees, human beings, frogs, everything. And so basically the structure within the atom, so this is, so basically we are human body, we are made of molecules, inside the molecule you have the atoms, and then you break that and you come to the nucleus, and then you come to the nucleons, like what the nucleus is made of, and so you keep breaking, and then the nucleon is made of quarks, which is bound by something called gluons, so that glues the things together, and you also have the electrons. So really going to the most fundamental, and this is around 10 to the power of minus 18 meters. So you are going to very minute scales of the universe. And basically so far, before the Higgs boson came into the picture, we had all of our matter particles and the force carriers between them. So for the matter particles, you have it's split into something called quarks and leptons, which is spread over 3 generations. So you have among the quarks, you have the lightest one of them, the up and the down quarks, and then comes into the second generation, a bit heavier, called the charm and the strange, and then came the bottom quark and something called the top quark. The top quark is the heaviest of the quark, it's 173 GeV. So it's even heavier than the Higgs boson. And for the leptons, you know electron, that's your friendly guy, like you know you have always dealt with the electron, and it has an associated neutrino called the electron neutrino. But then there are heavier brothers of the electron, something called muon, which is heavier than the electron, 106 MeV, whereas the electron is 0.5 MeV. So you can see how many times it is. And then the associated, the muon neutrino, and then the heaviest brother of the electron and also of the muon is called the tau lepton, which is 1.77 GeV, another order of magnitude higher, and tau neutrino, associated neutrino with it. In comparison, you can see the quarks, for example, of around MeV regions, and then for the charm it goes to say the GeV, and then it increases to say around 4.2 GeV, and then for the top it's 173. So the top was the last of the particles before the Higgs boson to be discovered, where it was discovered in a collider called the Tevatron in Fermi National Accelerator Laboratory. It's a lab just outside Chicago in the United States, and this was colliding at that time proton and antiproton beams at a center of mass energy, at a collision energy of around 2 TeV, and there it was producing these very heavy quarks in pairs, and that's how it was discovered in the mid-90s. How many were born in 1994? Nobody, I think. Nobody. Okay, that's when this was discovered. And then, these particles, these matter particles, there is a force acting between the matter particles, and there are different types of forces. So you must have heard about the electromagnetic force, which is basically your friendly guy, and the force carrier for the electromagnetic force is the photon. And say between two electrons, you have an interaction via the photon, which is called the electromagnetic force. So this is what you already know, but we'll come to the two unknown parts of the force, which is defined within our so-called standard model of particle physics, the strong force and the weak force. There's another force called the gravitational force, but this gravitational force doesn't come within the picture of the standard model of particle physics. So this strong force basically binds the protons and neutrons to form the atomic nuclei, or binds the quarks together to form the protons and neutrons. And for example, to the very fundamental level, if you go to the quark level, so what binds, I told you, is the gluon. It glues these different quarks, the up quark and the down quark, so to form, say, the proton or the neutron. So the proton is composed of up and down quarks. This is the valence quark composition of the proton, and this is bound by the gluons, and it holds and it's mediated, so the strong force is mediated by these particles called gluons. It's a very short range force. And then you have something called the weak force. This is carried out by some very heavy particles of the order of tens of GeV. It's called the W and the Z bosons. So of the 80 and 90 GeV particles. So, and these particles constitute the so-called weak nuclear force. So all matter particles feel this force. It's mediated by particles, which I just said, the W and the Z bosons. It's very short range because it's very heavy, and it gives us, it's basically officiates the so-called nuclear beta decay. It also gives us nuclear cycles, or powers our sun and other stars. So this is one of the very important, force of interaction. And then all this put together constitutes the so-called the standard model of particle physics, with the matter particles and the force carriers. So the leptons, the quarks, spread over 3 generations, and then the force particles, so the photons, the W and the Z boson, and the gluon. And the last to come was the Higgs boson, which will come later. So here is just different particles which we just saw, all these, and their discoveries over the years. So, but before we come to the Large Hadron Collider, where we are at this moment, let me give you a very brief picture of from where we started. First we started discovering all these particles which I just showed over the years, and then before one of these large accelerators were built, we stopped in 1982, 1983, with the discovery of the W and the Z bosons. And this was at CERN as well. So once we discovered the W and the Z bosons, we thought of not only, having a clearer understanding of what these heavy bosons were about, of what these heavy bosons are, their properties, and how it can affect our understanding of the universe, or our understanding of matter, force, interactions, everything together. So for that, we built another collider. And this collider was an electron-positron collider. This collider was built at CERN as well, and it was built basically with the energy exactly at the threshold of production of the W and the Z bosons, so that you produce these particles in surplus to have clearer understanding about the properties, the characteristics of these particles. Only then you can, in science, when you see something, you have to understand the characteristics, the properties of what you observe. And then you can infer onto something, okay, this is what we have observed. From your observation of these different properties, you conclude something after that, you infer something. And this is why that collider was built. But that collider, which is this large electron-positron collider, so basically first it started with 46 GeV of electron and 46 GeV of positron, so just colliding at the threshold of the Z boson production, and the W boson mass was lower, so in any way it was being produced. And then once we achieved that, we went to higher energies in order to find the Higgs boson and other particles which can constitute physics beyond the standard model of particle physics. And so we went to 104 GeV of electrons and 104 GeV of positrons. And this was colliding in the same tunnel that you saw for the Large Hadron Collider, that 27-kilometer long ring, this electron and positron. And there are 4 different types of detectors, 4 different detectors, or 4 different experiments, as you can say. And these 4 different experiments were operating to independently to observe these collision events, to have a clearer understanding of the W boson, the Z boson, the strong force. So basically the quarks coming out and how they are forming, particles. And so these different properties, but also, trying to discover our unknown Higgs boson at that time. And the lab was very successful, in fact, in excluding to the very low mass ranges of the Higgs boson to where we are. And then there was also a collider at DAISY. This is a collider called HERA. It was operating at the Deutsche Elektron Synchrotron in Hamburg in Germany, and this was to understand the structure of the proton. So how do you understand the structure of something? By observation of what? No. Have anybody heard about Rutherford scattering? Okay. So what is Rutherford scattering? No. What experiment? Yeah, but what do you do there? Right. Right. Okay. Yeah, so that's how you understood the structure, right, of the nucleus there. Yeah, but why electron? Why not a proton being thrown at the gold foil? I can have a positron also, no? Instead of an electron. That's also positive. See, we want to explore something that is not known to us, that is the structure of the proton. But if I first collide a proton with a proton, means I'm colliding an unknown with an unknown. That's not the right way to go first. We can do that experiment later. The first thing would be following what Rutherford did. An electron is structureless. It's a point particle. So you hit with a point particle, something more complex, which is inside, right? So basically the proton you can imagine as a garbage box with full of junk inside. An electron is just one of that junk, which will not break into, okay? And so this was being explored, the structure of the proton at the HERA collider at DAISY in Hamburg. And then there was also at the same time, in the 90s, as I just mentioned, the discovery of the top quark at Fermilab. Fermilab was, as I mentioned, another laboratory outside Chicago in the United States, and this is called Tevatron. This accelerator, this was colliding proton and antiproton beams at a center of mass energy around 2 TeV, and there were 2 experiments operating called the CDF and the D0, and they independently discovered the top quark. It's very heavy quark, the heaviest of all the fundamental particles. And then after years of effort, came into existence the Large Hadron Collider, which operates in the same tunnel as the Large Electron-Positron Collider, the LEP, and this was designed to collide particles at 7 TeV each, so at a center of mass energy of 14 TeV for head-on collision. At the moment we are operating at 13 TeV. We have not yet reached the nominal collision energy, so we are colliding proton beams each, and there are 4 experiments operating: ATLAS, CMS, LHCb, and ALICE. So you just heard about accelerators. So the acceleration is basically force equal to charge into the electric field, where the accelerating voltage is 5 megavolts per meter, and then it's guided, this beam is guided in a circle by the Lorentz force with the magnets. And you have just heard about all this in the previous talk, but I will move to more of the physics part here, that why do we accelerate particles. I think this is something very interesting for you to hear. You can discuss probably in the interactive session with each other as well as with me. That's the best part. We'll come to an interactive session. We'll come, you can stop fighting. So we'll come to an interactive session where you can discuss with each other, and you can talk to me as well if you want to. But I think it's very important if you can try to understand why are we doing all these things. So we accelerate particles to very high energies and let them collide. But why? It's not that today one fine morning I wake up and say, oh, I just want to accelerate a particle and just want to collide it and observe, not observe, but just have fun with it. It's not like that. We collide to study what happens during an interaction at a very minute length scale to produce new particles, thanks to Einstein's E equal to mc square. So the higher the energy we collide, basically we produce these high mass particles. And so basically studying the produced particles, how many they are and their characteristics, we can understand what happened at the instant of the collision and extract the fundamental processes that regulate nature. And why do we have to accelerate? Because, say, if I collide something, with our eyes we can see dimensions 10 to the power of minus 2 centimeters. That's it. But you saw at the level of quarks 10 to the power of minus 18 meters, right? So there's something which you are not aware of at this moment. So you are aware of simple mechanics of larger objects, but there is also something called quantum mechanics. So this is mechanics of these very tiny particles, this length scale of 10 to the power of minus 18 centimeter, minus 15 centimeter, minus 16 centimeter, and so on. So this very minute length scale, and at that scale, this mechanics tells us that a particle, or say, for example, light, what you see here, this light, it has a double role. It behaves as a particle as well as a wave. Very good. So basically, when this particle behaves as a wave, means it has a wavelength. And this wavelength is something which is equal to, there's a constant called h over the momentum, which means the higher your energy of collision, the deeper you can go into the length scale, just because it's inversely proportional. So the more you can penetrate into, the more you can see into. So the higher the energy is, the smaller the wavelength, and therefore the smaller the dimension we can explore. So just to give you an idea, that the electronic microscope can explore region of 10 to the power of -6 centimeter, so as the cellulose of DNA to go beyond, so say 10 to the power of -15 centimeter, we need to accelerate these particles. This is the reason why. And then we saw, for example, the large electron-positron collider. These were 2 point particles, smashing into each other. But here we are not colliding electrons and positrons, 2 point particles. We are colliding 2 protons. So each of these proton is made of, say, up and down quark with gluons inside, and these gluons further splitting to form a quark and an antiquark, and then recombining, and then again splitting and recombining, and then it forms a sea of quark and antiquark pairs with these 3 valence quark composition. So it's basically a broadband quark-gluon collider. So there are lots of so that's why I mentioned it's like a garbage bin. So you're colliding 2 garbage trucks, I would say, with very high velocity, and then boom, and everything like smashing into each other, and so this quark, gluon, quark, gluon, everything smash into each other. So, and in particle physics, so you must have heard this term called Large Hadron Collider. But what is a hadron? A hadron is a composite particle made of quarks held together by the strong force. The hadrons are characterized into 2 families. It's called baryons and mesons. The baryons are like protons and neutrons. They're made up of 3 quarks, and the mesons are like something called pions and so on. They're made up of 1 quark and 1 antiquark. So far what you have seen is till the point of collision. Now let's come to what the Higgs boson is. So the Higgs boson is something that doesn't exist as a particle, as an entity in the universe. There's something called the Higgs field. In simple words, what you can say is a Higgs force, in simple words. Okay? So it's like a force which, the Nobel Prize winner Peter Higgs had predicted, and it invades all of the universe. And now, basically, in this force, when the particles, what you are seeing like electron or proton, the fundamental particles like the electron or the quark and so on, when they enter this force, when they interact with this force, so the force of that particle, when they interact with the Higgs force, that interaction gives the mass of this particle, like for the electron or the other particles, fundamental particles. So you can imagine that it's like a swimming pool. So that swimming pool is, so in a swimming pool what do you have? You have water, and that water is like, say, the Higgs force. And now you start to walk in that swimming pool, and you suddenly enter the swimming pool and you walk, and if you could not see the water, you could think to have become suddenly very heavy, because you're not walking in the air, you are just walking in a swimming pool. So there's an interaction of your body with that body. So you have gained, you can imagine then that you have gained mass, because you can move, you have become heavier. And so that interaction with the medium around you, so this is exactly what is happening for the particles which gains mass from the Higgs field. So the Higgs field is equivalent to the water around you in the swimming pool. So here I'll give a very simple description of what is happening. So we can think of the Higgs particle as the messenger of the Higgs field. So basically, you can imagine that this is the Higgs field here, and the penguin, which is moving very smoothly. So there are different particles which you saw so far, different fundamental particles, and they have different masses, right? Now these different masses means, for example, the electron has the lowest mass, 0.5 MeV. The muon has a higher mass, or say the top quark has the highest mass, 173 GeV. So basically the mass of this particle is how strongly or weakly the force of that particle is interacting with the Higgs force or the Higgs field actually. So in quantum mechanics or in particle physics, we call it a field instead of force, like this is the terminology. So this is like the top quark. You see it's somehow dragging itself because it's very heavy. So maximum interaction. But this is the electron, which is like a penguin just sailing into it. So the minimal interaction. So basically it has the lowest mass. So this, along with the Higgs boson, makes up our full standard model. So this new Higgs field is responsible of the elementary particle mass and has a particle associated to it as well. So the Higgs interacts with the Higgs field itself, and this self-interaction gives you the mass of the Higgs boson and that Higgs particle. And this can only be observed in a collider, in a collision. And the direct observation of this particle is necessary to confirm that this hypothesis or this force existing is correct or not. And it was the only missing piece. And in the standard model, the Higgs boson must have a mass smaller than 1 TeV in order for the theoretical particle physics, or for the theory to correct, to save something called unitarity, which you don't need to know at this moment. But okay, but all these predictions and all this goes back to really historical days, 1964. So this was long ago, when Peter Higgs was awarded the Nobel Prize. He was instrumental. He, along with other physicists, François Englert, who actually received the Nobel Prize in 2013 along with Peter Higgs, they independently came out with this theory that for particles to gain mass, there is some force which interacts with the force of that particle, and the Higgs, and this is called the Higgs force. It was named as the Higgs force after Peter Higgs, of course. So it was, but Peter Higgs predicted that there is a force, and this force interacts with itself to give a new particle which will confirm the existence of this force, and this new particle is called the Higgs boson. And then, once this was done in 1964, scientists started scratching their heads, and they started, thinking, okay, how to observe this Higgs boson. So at that time, there were lower energy, experiments, but through different means, scientists started to explore for this Higgs boson. But one thing I'll tell you, something very interesting. What Professor Higgs, he, though he, put this theory forward about the Higgs boson, he did not predict the mass of the Higgs boson. The Higgs force itself gave the mass. So the mass of the Higgs boson was not known. So it could go from anywhere from very low to very high. So even in low energy experiments, people started searching at that time. But then, a roadmap had to be cleared, because one had to, explore high energy regimes. One had to look for this fundamental particle. And this person you saw, you see, he is the grand old man at CERN. His name is John Ellis. He has retired, and he, gave a phenomenological profile of this Higgs boson, the roadmap, and it's very interesting actually. He said that for reasons we do not want to encourage big experimental searches for the Higgs boson, but we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn up. So basically the theorists at that time, they were scratching their heads how to get this Higgs boson, and once they were unsuccessful in, coming up with some ideas, he, as the grand old theorist, he just put the ball into the experimentalist court, as you can see. That is for you guys, I'm an experimentalist, so they just threw the ball in our court. It's for you guys to explore how you explore, but this thing should exist for the mass to, for the mass of the particles to be there. And then the roadmap had to be built. And then came this large electron-positron collider. But what was happening is scientists started looking for this Higgs boson, or this particle, from very low mass to very high mass. It can be anywhere till this 1 TeV, starting from very low mass. And with this large electron-positron collider, scientists could exclude Higgs boson masses below 114 GeV. Exclude. What is the meaning of exclude? Exclude means you start looking for this new particle. But so it's like, you are performing an experiment. You have signal and you have noise. What's the background? Okay. Now, when you perform an experiment many times, like statistics, you toss a coin many times, so it's just like that. So, and then you don't observe something what you want to observe or what you want to see with a lot of statistics, you start excluding that. So then below that 114 GeV, that region was starting to be all excluded because there was nothing, no observation connected. Above, no, that could not be done. And why it could not be done? Because the energy of the large electron-positron collider was such that it could not go above that. It could not go above that because if you can recollect, it was increased to 104 GeV per beam. Okay, 104 GeV per beam means you just add up 208 GeV. Now the mass of the Higgs is 125 GeV. You might question, why was it not discovered then? Because in that scenario where electron and positron is colliding, the Higgs boson is produced in association together with something called the Z boson, which you saw, via this interaction. Because electron and positron is a positive and a negative particle. It goes in, produces a neutral particle, and then it goes out again to form, say, a Higgs boson. But along with the Higgs boson, there has to be a neutral particle. Now, what can be this neutral particle? So the maximum likelihood for the neutral particle to be there should be a very heavy particle. Why? Because the Higgs strongly interacts with the heaviest particle, right? So the maximum likelihood for a neutral particle will be the Z boson, which is the heaviest of neutral particle within our standard model of fundamental particles. And no other particle is that heavy. So then but the mass of this Higgs, Z boson is 91 GeV. So if you add 125 and 91, it's more than 208 GeV. So we are just short around of 10 GeV. So, but nobody knew the mass of the Higgs boson. So in the 1990s, if this large electron-positron collider had just 10 GeV higher in mass, the Higgs boson would have been discovered, 15 years ago, in 1997 or 1998, not in 2012. So this was really something we didn't know. We are performing an experiment, we are exploring an unknown regime, and we just fell short there. But that's okay, because at that time, I was in high school. I could not have performed my PhD thesis on the Higgs boson and the discovery of the Higgs boson. So it was good for me in that way. So then, in the 90s, CERN took that initiative. CERN took that initiative because in the 80s there was another collider which was a 40 TeV proton-proton collider, It was called the superconducting super collider, which was being built in the United States. And believe me, around 35% to 40% of the construction of work for that was almost done. And suddenly, the American government decided, no, we stop the project. And diverting some of that money to other projects like NASA, and also there were some comments from some condensed matter solid state physics people. You can observe this kind of mechanism in small condensed matter system. You don't need to observe a Higgs boson for that, but that's not true actually, because the Higgs field for the Higgs field to confirm, you need to observe this particle, the Higgs boson. And then CERN took that initiative, said, okay, United States has stopped it, fine. That was in the late 80s. In 1991, in the December CERN Council meeting, it was thanks to the great push by the CERN Director General at that time, Carlo Rubbia. So Carlo Rubbia was another Nobel Prize winner for the discovery of the W and the Z bosons in 1983 at CERN. And so basically, Professor Rubbia, he put this forward that the Large Hadron Collider is the right machine for the advancement of the subject and the future of CERN. And he was very right, actually. So in 1993, the superconducting super collider was formally cancelled after lots of deliberations. And this proposed 40 TeV PP collider at Texas, and due to so-called budget issues, but really there were no such budget issues. And then in 1993, in the December proposal of the Large Hadron Collider with commissioning in 2002, it was proposed that the Large Hadron Collider will be starting in 2002. But you see, what we envisage that it will start, we always start much later. 2002 was the commissioning, the starting, prediction, but we started in 2009. 7 years later, because it's such a complex project. It's not that what we think it comes out to be that. There are lots of engineering, technical challenges. It all comes part of the package. And then in the 1994 June Council meeting, so this council meeting is something the administrative and the scientific community meeting at CERN. It takes place every 6 months, and there all the policies of CERN are discussed and decided, which is headed by the CERN Director General and the President of the CERN Council. And a stage construction was proposed by the then CERN Director General. He was from UK, Chris Lillian-Smith. But some countries could not yet agree because it was a lot of money. So the council session vote was suspended until the next council meeting in December, the 1994 council meeting, where a two-stage construction of the Large Hadron Collider was approved. Two-stage construction because of money, finance issues. That, okay, you construct this first and that first. But then when this was proposed in the 1994 council meeting, at that time only the European countries were involved. But a two-stage construction of the Large Hadron Collider was not necessary, because after that came United States, Canada, India, Japan, all the countries came together. So it's like a really multinational, all around the world, people came together contributing to this project, and this project was done at one go instead of this two. And just to give you an idea, so this CERN Director General, Chris Lillian-Smith, is actually also a distinguished professor at one of the Department of Atomic Energy Units, which is NISER, National Institute of Science Education and Research in Bhubaneswar. So in 1990, this was, some studies were made in Germany in a workshop called Aachen, and there some discovery potentials of how the Higgs can be searched, how the Higgs can be discovered was proposed here. And then it took 20 years since then, from 1990, for projecting, constructing, simulating all these. And then you can see the years of design, construction, and commissioning of the Large Hadron Collider. And these were being inserted in these tunnels, and all these pipes and magnets, as you can see. Stop working. Okay, and the largest cryogenic system on Earth. This was a huge engineering achievement, and then it took years of design, construction, and commissioning for these experiments. So you see the installation phase which is going on. This was in 2004, and then these are for the accelerator part, but then comes the detector part, and you can see the empty cavern. So where these things meet, there you, as I said, you place the detector. The detector is like your camera, which pictures all these particles which come out of that collision, and this has to be placed around. So basically you have to build a huge cavern, and these caverns are sizes of 30-40 story building. It's not so small. So, and you can see the empty cavern here, but then the most important thing is these detectors were built like say it's a huge, say, CMS or Atlas. These are the two huge experiments, but there are different sub-detectors which will be coming to, and these sub-detectors were built, assembled outside, but then whole of the detector cannot be assembled, like all the sub-detectors together cannot be put together and inserted into the cavern. Why? Because you do not have a crane which can handle that weight and just put it into that cavern. So you have to put in bits and pieces inside and assemble everything inside. There's no crane in this world which can take all of the detector assembled together and just put it in that cavern. That was not possible. So you can see parts of the detector being inserted into the cavern, and as I just mentioned, the two major detectors were Atlas and CMS. Atlas, like it's a detector twice your Vidhan Sabha. You are coming, and CMS is a smaller sized detector compared to Atlas. The reason is, I'll just show in my next slide why CMS was smaller than Atlas. And then you have two other experiments called ALICE and LHCb. And this is, and in India actually we have the two collaborations, the CMS and ALICE. ALICE is another experiment, and CMS, which is the huge experiment with 5,000 physicists, 5,000 members in fact, so 1,900 physicists, around 1,800 students, around 1,000 engineers and technicians, which who are very crucial for the running of the experiment, for the operations of the experiment. And they come from around 200 institutions from 43 countries with one goal: to unveil what our universe is made of. And this is in India, the India CMS collaboration. So at first I put my institution, which is Indian Institute of Science, Bangalore, and then you have Tata Institute of Fundamental Research, which is the Department of Atomic Energy Unit in Mumbai, and then Bhabha Atomic Research Center, IISER Pune, Institute of Physics Bhubaneswar, Delhi University, and so on. So all the different institutes coming, and this is a very small fraction of the CMS collaboration. So this is not India CMS, but it's very small, tiny fraction. It's so huge, it's like a township, 5,000 people. So you go to a village, I don't think you will find 5,000 people maybe. So, so just imagine per experiment 5,000 people. So 5,000 from CMS, 5,000 from Atlas, and then there are like say 1,500 from LHC, 1,500 from ALICE. So 13,000, plus there are other experiments running at CERN. So 2,000, 3,000, 4,000. So there are like 17,000, 18,000 people working at CERN. So really a huge town, you can say. And this was in late 2004 in the underground the cavern, which I was just showing, so the magnified view. And then lowering slowly, you can see with the crane bits and pieces into this like 30-story cavern, and then assembling all these sub-detectors together. And then this is insertion of the innermost element. You can see shining, and it's the tracking system of the detector for the charged particle tracks in the detector, the trajectories, and this is made of silicon. and this is the setting, before everything comes together, the setting of the detector. CMS ready to close. Now let's close it. But before we close, let's just go into what the detector is. So which I just promised you. So as you go from the inside to the outside of the detector, you first come across this tracking system, which which is around the beam pipe, which is responsible for the charged particle trajectories. You have a trajectory because you have a magnet, so there's a bending. So any charged particle will bend and show this trajectory. You can find the momentum from there, and then around that you have something called calorimeters. Now calorimeters are you must have studied, like, calorimetry is like energy, right? Energy measuring. So here also the concept is the same. The tracking is detectors are measuring the momentum, and these calorimeters, they are measuring the energy of the particle. Means you have to have all the energy of a particle deposited in that detector called calorimeter to have the full energy deposit, or to have the full energy that was carried by the particle. It cannot be that you measure partial energy and it's gone, then you cannot know what it is. You cannot reconstruct two particles and say, from the decay of, say, another giant particle, and say, what that giant particle was, if only partial of that energy. So means you have to either have a very dense, material, so that all the energy gets deposited. This is why CMS is smaller than Atlas. So Atlas has a less dense material than CMS, which means Atlas have to be huge, bigger, because the penetration would be more than CMS. CMS much more dense, so it can afford to be a bit smaller, and all the energy would be deposited, and it all depends on the density of that. And then, as I promised, we're ready to close, and then the first collisions, which were observed on the 30th of March 2009. This is the control room in CMS. This was the CMS spokesperson, Joe Candela, who announced this discovery of the Higgs boson. He's a professor from University of California, Santa Barbara. He is a very famous person at CERN, Albert Duroek, and so there are so many all famous people around, in that control room to observe the first collision. And I would like to mention that Albert Duroek is a very senior staff scientist at CERN, and he was visiting us here at the Indian Institute of Science a couple of years ago, and he will be coming in January or February again next year on my invitation. So he's one of the, and he was the Higgs, this group convener who was responsible, who pioneered, in the CMS experiment, the discovery of the Higgs boson. It was during his tenure, under his headship, leading this Higgs group, because there are so many in this huge experiment called CMS. There are so many physics we are targeting, so many things we are looking for, and Higgs is just one sector we are looking for, and he was heading this sector actually at that time. And then when the first collisions happened on 30th of March 2009 of these proton beams, so in the New York Times, what was reported, you see it here in small, particles collide and champagne glasses click, right? So this was a moment of joy, a moment of celebration. But okay, this was a moment of celebration in the United States, in Japan, in Europe, all the European countries, everywhere. What was happening in India? Particle physicists were celebrating. Accelerator physicists were celebrating. Finally, we have got things right. Okay? But then, in the Indian newspapers, media, before everything started, they were saying, oh, there will be an earthquake, everything will be, or huge, everything will be destroyed, the whole, and at that time, I was doing my PhD in France, in the French Atomic Energy Commission, and my mother called me up, and before the collisions happened, and she told me, oh, I heard that you people will die, and there will be a huge disaster there. I said, who told you? She said, it's all over the news in India. I said, you just forget, you relax, you sleep. I mean, so this is the thing that was happening in the Indian media and the newspapers, as always, and then once these collisions happened, let's come to this colliding beams. So you have these two beam pipes, which circulate in opposite, and these two beams. So this 27 kilometer long beam pipe. So there are two beam pipes. And then the two beams of protons, they circulate in opposite directions. They meet at one point where they collide, where they interact, and these beams, which are made up of, you see, these 1,380 bunches of, and each bunch has around 150 billions of protons, and the bunches cross at 4 places, which are these 4 experiments or detectors, but then you see 150 billion protons crossing 150 billion protons. So let's say 100 billion protons crossing with 100 billion protons. But only 20 to 30 out of this 100 billion, only just 20 to 30, so 30 pairs of protons collide with each other. They smash into each other and they break apart. The rest, 100 billion minus 30, they just pass by each other and say hello to each other. And they just say hello and they just pass by, but they don't, quarrel or fight with each other. Only these 30 fight with each other, they collide with each other, and once they collide, as I said, it's like 2 garbage trucks colliding at high velocity with each other, and then it breaks apart. Everything breaks apart, and with that energy, particles start coming out. Splash of particles. And what is our goal? Out of that 2 garbage trucks, when everything breaks apart and there is like a lot of garbage around, we have to find that really tiny golden particle, which is the rarest of rare artifact out of that huge mess. And this is what we are struggling for. And for that, we have our camera, which is the CMS detector. And the CMS detector is really like a camera with 80 million pixels. It's obviously no ordinary camera. Why? Because it can take up to 40 million pictures per second. Your Canon or whatever camera you buy, it cannot go with 40 million pictures per second. The pictures are 3-dimensional. I think nowadays you can get some 3D pictures now, but I just saw on Facebook one of the professors who is my friend on Facebook from University of California, Davis. She just posted her anniversary picture of 3D picture. But these pictures are 3-dimensional, and the weight of that camera is 30 million pounds. So it's not a portable camera that I just pick up and take a picture. It has to be static, So, and the problem is that we cannot store all the pictures we can take. So we have to choose the good ones, which we need to find that rarest of rare artifact. We have to do this really quickly. Why? Because the things are happening very fast. So we cannot wait longer. We have to have some strategy. So these are the experimental challenges we now come. So the collisions are frequent. The beams cross 16.5 million times per second, and about only 20 to 30 pairs of protons colliding. So the interesting collisions are very rare, and less than 1 per 10 billion for some of the most interesting ones. We can record only about 400 events per second. That is what we can record. So we have to choose them out of that huge mess. And we must pick the good ones and decide very fast. And for that, we had to create something called decision levels, which is called trigger. We have to trigger on something to choose. We have to make this decision. So these decision levels. So first analysis is done in a few millionth of a second and temporarily holds 100,000 pictures. A final analysis takes 0.1 second, and we use 10,000 computers, and we still end up with lots and lots of data on disk. Lots and lots of data. And just to give you an idea, that 22 petabytes of data was collected. So what is petabyte? It's 10 to the power of 15. It is 10 to the power 15 bytes of data in 2011. So that was when the lowest amount of data was collected, and more will be increasing, and you can imagine how much. And for that we have lots of storage systems which you just heard in the previous talks. So something called tier 0, which is for the recording of the data, the reconstruction of the particles and the distribution. And then in tier 1 you have the permanent storage, the reprocessing of the data for finer, refining the data. So it's like, your mustard oil and then refined further. It's something like that, So it's sieved further, and then a first level of analysis, and this is in tier 1. And then in tier 2 you have the simulation and the end user analysis. So for example, I want to look for the Higgs boson, and I have to say Higgs decaying to some particles, and I do it here. And this is in an international collaboration to distribute and analyze this LHC data. And this is something called the grid system, which you just heard. So it's a huge computing system, and it's distributed all over the world, starting from North America to South America to Europe to Asia. You can see Korea, China, Japan, India. You have in Mumbai. And then it goes all the way to Auckland in New Zealand. Here you can see. And the first LHC runs you can see in 2010, 2011. More events started accumulating, and then in 2012 you can see more and more interaction when the number increases. And here, with all this data collected during this juncture, around July 2012, we announced the discovery of the Higgs boson with a data collected of collision energy 5 inverse Femke-Börner of data, some amount of data collected, all of the data collected in 2011, and a part of the data collected in 2012. With that, we found, or we discovered, the so-called Higgs boson. So 7 and 8, and this is a picture. So you have the Atlas detector here. Opposite, you have so the Atlas detector is on the Swiss side. The CMS detector is placed on the French side, and then near the airport of Geneva you have the LHCb experiment, and here you have the ALICE experiment. So these are 4 experiments which are operating. And then from 7 to 8 we went to 13 TeV. 13 TeV, which is the collision energy which we are operating at this moment, and we'll go further higher to the nominal energy, which is 14 TeV, and that can take place any time in the next 2 to 3 years timeline. There are lots of challenges in the experiment. One is this challenge of the triggering challenge, the decision-making challenge, the how to select this 400 out of 20 million events per second. This is one of the most important challenges, and while keeping the interesting physics. So when we select this 400 events, we should not throw away our rarest of rare artifact which we are looking for. We have to make the best effort to preserve that out of that huge mess, that huge garbage. And then the computing challenge, how to reconstruct, store, and distribute these 400 increasingly complex events per second, so over 100 picobytes per experiment. And then the analysis challenge, that maintain the particle reconstruction efficiency, the identification efficiency of these different particles at this highest rate of interaction, where you have where you can see this kind of multiple collisions happening. So here you have to select, reconstruct your particles in this mess. It's challenging. It's a huge challenge, because as I said, like 30 pairs of protons, they collide, and then it's a mess, complete mess. And from there you have to reconstruct each of these individual particles. And for that we have our detector, where we identify all the stable particles produced in the event, stable particles, because the unstable particles decays to the non-stable particles, and then combining the capabilities of each of the sub-detectors which I just mentioned, tracker, calorimeter, all this. So, and then we link our identification in tracker with the calorimeter and see if we can identify a particle, just like here, for example. So this is a transverse section of this detector where you have the silicon tracker, and then we have the calorimeter, and then we have the magnet, and then we have something called the muon, which you just saw, the muon detectors outside. So basically, for the muon detector, it just reaches up to the muon with a trajectory, fine, in blue. In red, you can see this is the electron. So the electron is a charged particle. The electron will have a trajectory in the silicon tracker, but then the electron is also an electromagnetic particle. So when it enters the electromagnetic calorimeter, it has to deposit certain amount of energy, not certain amount, but full of its energy, so that the energy of that electron is known. So once it deposits all the energy, and if that energy deposit, which we see in the calorimeter, can be linked to this charged particle track, means it came from the same particle, which means that's an electron. The trajectory pointing to an energy deposit means that's an electron. Whereas for the photon, you will not have a trajectory, because it's not a charged particle, but you will just have an energy deposit in the electromagnetic calorimeter. And then for a charged, say a hadron, like a pion, you have a charged trajectory, but then it goes and puts all of its energy in the hadron calorimeter, which is outside the electromagnetic calorimeter. For a neutral hadron, you will not have any trajectories. That's why I put by dashed line. You will have all of its energy gone into the hadron calorimeter without any trajectory, means it's a neutral hadron. And this is for a photon, electromagnetic energy deposit without any trajectory. So this is an overall picture which I just mentioned. So now we come to the really, after all this, after knowing what are the challenges for this experiment, what are the detectors, how the particles are reconstructed, these are the most crucial aspects before we go to discover the Higgs boson. Because the Higgs boson just didn't come like this. It came after understanding each and every phase of the experiment, from the construction to the commissioning to the understanding of the detector to the understanding of the particles to the reconstruction of the particles, understanding the performance of these particles. And then once we know, because see, the Higgs is Higgs has a very small lifetime, 10 to the power of minus 21 seconds. Means once the Higgs is produced, it immediately decays, and it decays to these stable particles. So we have to first understand the stable particles before we can even go and reconstruct the Higgs from its decay. So all those first we had to do. Those were the challenges out of that huge mess of collision you just saw. So we enter the Higgs journey. It's called a journey. It's really not a destination. Why? Because once we discover a particle, it opens up larger questions. Why? What are the characteristics of the particle? Is it consistent with some theory? Does it deviate from certain theory? And then can there be more Higgs boson? Of course, because the standard model of particle physics which you just saw, it's really not a complete model. So there are several theories even beyond the standard model of particle physics, and we are just trying to open up different avenues in that direction and explore different avenues and then once we start discovering more and more particles, we have to join everything together to form a complete theory which will join our known standard model and well verified standard model of particle physics at this moment with something which we do not know so far beyond the standard model which we call. Right? So so that's why I say it's a journey, it's not a destination yet. So our discovery doesn't finish there, it just opens up more questions. Even the mass of the Higgs boson, why is it 125 GeV? The spin, the parity, everything, like, you know. And okay, sorry, what is happening? Okay, so I should tell you that Peter Higgs posed for this very simple man, you know, this he was very ashamed after this, because this picture was used by one and all for different seminars, and he said, oh, I should not have posed for this. You know, he felt very shy after that for this. You know, I should tell you something, that at CERN, it's a kind of a different environment. Like, say I'm traveling from CERN to the center of Geneva by tram. I'm sitting in a tram. Beside me sitting is a Nobel laureate. I don't even know him. Starts chatting, I start chatting, and then we go all the way. It's a say 25-30 minute journey to the center of Geneva, and suddenly after 20 minutes I tell him, what do you do? And then he says, oh, you know, I don't do anything now, but you know, on this year, on this, I won the Nobel Prize for this. So, wow, I mean, but that's simple, you know. Or the CERN Director General would be coming tomorrow. She will be delivering a public lecture tomorrow. And Fabiola Gianotti. Fabiola Gianotti, say I'm sitting in the CERN cafeteria for lunch. She comes, takes a tray, takes her food, comes, sits alone, takes her food, and then puts the tray back to the place where the tray needs to be put, like, you know, our plates, and then goes back to her office. There's nobody hanging around her, and nobody, and she's and nobody even to take her plate away. Like, you know, you come, you take your own food, you eat, and you just go. That's it. Like, you know, it's that simple. Like, so, and so in 2013, the Nobel Prize in Physics was awarded for the discovery of the Higgs boson at CERN in 2012, and it was awarded to the two proponents, Peter Higgs here and François Anglais from Belgium, and Peter Higgs from Scotland. And you know, interestingly, these two physicists who had independently proposed this idea, and so much of effort has gone into it, they are meeting for the first time ever during the announcement in 2012 at CERN. They had never met each other. It's a very interesting, yes. And so in 8th October 2013, the Royal Swedish Academy of Sciences decided to award the Nobel Prize in Physics for 2013 to François Anglais and Peter Higgs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at the CERN's Large Hadron Collider. So, and they were in deep discussion, like, you know, but one of my friend was telling me, he's he's also a faculty member, so he's in Europe, and he was telling me what in India we say, that they were doing tutu meme. Means he was saying, oh, I discovered first, he was saying, no, I proposed first, but both proposed at the same time independently. You know. And okay, now let's come to something more serious. So these are called something called Feynman diagrams. So this is for the Higgs production. As I told you, this is a broadband quark-gluon collider. This is what I told you. So there are quarks, gluons. So the highest probability or the highest rate of production for the Higgs boson is via the fusion of two gluons when the protons collide. And then comes something called vector boson. So this W and the Z bosons fusing with each other, and then comes you know, in associated production of the Higgs with the vector bosons in Q bar, say quark anti-quark going to a W or a Z boson and a Higgs boson, and then the last of it, the smallest contribution comes from the top quark fusion to the Higgs boson. So a gluon fusing and then splitting into top and anti-top. So basically a gluon splitting to top anti-top, and then top anti-top fusing to form a Higgs boson. So this is the lowest and this is the highest rate. And then, as I just mentioned, that the Higgs decays because the lifetime is extremely small, 10 to the power of minus 21 seconds. Oops. Here. So, and it decays to different fundamental particles. The highest among them is decaying to bottom quarks, BB bar, which you saw had a mass of 4.2 GeV with almost 60% branching fraction. Then you had decaying to W bosons, then Z bosons, and then the smallest is decaying to, then you have decaying to tau leptons, and the smallest decay is to photon pairs. But then when the discovery was announced, interestingly, the discovery came from the Higgs boson, the observation of the Higgs boson decaying to photon pairs and this Z star. So basically the Z bosons decaying, and then the this boson actually splits into further into lepton and anti-lepton, which means L plus L minus, which is electron positron, E plus E minus, or mu plus mu minus. And why, interestingly, though these had the smallest of the branching fractions, the discovery could be announced in these two modes rather than these modes because of the fact that the photons and these electrons and muons were very cleanly detected within the detector, very precisely. Whereas your decays to bottom quarks, the quarks are never seen in the detector as an independent entity. The quarks have something. The quarks and gluons are fundamental particles which have a property called color. It's a quantum number which is called color, and that color cannot be observed in nature, so it's confined. Confined means the quarks basically form hadrons to be observed. Now, when we are working in a hadron collider and we are trying to observe this quark forming a set of hadrons, out of that huge amount of hadrons there, it becomes extremely challenging, difficult task. It's like finding a special garbage piece out of all that garbage which you have collided and which have come out. One of the special garbage pieces. It's not like the golden needle. It's like one of the small garbage piece out of all that garbage piece. So that's why this was the most. And then next came these, and this discovery came last. So here in the detector you can see the Higgs boson decaying to a pair of photons. This was energy deposited in the electromagnetic calorimeter, and then these were all tracks like splash of events, and this is how the Higgs was reconstructed. There were around 500 Higgs events at that moment when this discovery was made. And this is Higgs decaying to ZZ to 4 leptons. So here you can see the Higgs decaying to ZZ, one of the Z decaying to 2 electrons, another decaying to 2 muons. Here you can see the 2 electrons, here, here. So you can see a trajectory here, and this trajectory is pointing to an electromagnetic cluster. So these are the 2 electrons, and in red you can see the 2 muons in the muon chambers, but they also have a trajectory because these are charged particles. Here. And here you can see the Higgs decaying to 4 muons. So this decays to 2 muons, another decays to 2 muons. So basically you have 4 muons coming out with different momenta, of course. And then finally, the discovery, the Higgs boson on the 4th of July 2012. But before you go even to this discovery here, what was happening, I told you, the Large Electron Positron Collider had excluded below 114 GeV that nothing was existing there. Then there was another collider which I said at Fermilab, the Tevatron. The Tevatron excluded a small range of mass around 160 GeV from 145 to around 175, 180 GeV. That window it had excluded. When the Large Hadron Collider started, it started excluding from 145 to all the higher mass region till 1 TeV. That was the first thing the Large Hadron Collider did, the CMS and ATLAS experiment. Then was left that small window from 145, means what? You did not observe anything interesting there. But then the small window of 114 to 145 was left. And then both these experiments, CMS and ATLAS, started closing in on the fugitive. That, thief, or that, you can say. So that fugitive, that criminal was being targeted there. Okay, so the police started closing on the window, narrowing the gap, and CMS then excluded below 115. From 114 it went to 115. And then from 145 this window it came down to 127. Then there was and it was getting very, very interesting. Also, it was becoming a very anxious moment. That CMS had a very narrow window now remaining between 115 and 127 GeV. And this window could not be excluded. Why? Because something interesting started popping up. Something beyond our expectation started coming. And then we started narrowing further, and it came to a point where in mass spectrum, invariant mass spectrum, because the photon is massless but it has energy, right? So when you know the energy and the angle between them, you can reconstruct the invariant mass of the diphoton pair. And here above the background, this is your background or the noise what you should have, and here started popping up certain interesting events. That small bump, and the small bump is basically your Higgs boson, the discovery of the Higgs boson. The Higgs boson decaying to 2 photons, which is that rarest of rare artifact now, which has come out of all these events, because this is the whole set of events you have. And that small bump, this tiny thing, is your Higgs boson. That's the discovery moment. Look for an excess of events in 2 photons in the mass spectra of these diphotons, and I just showed you this. And then and if you just zoom in, this is what you see. This with the magnifying glass. And this is similarly for the 4 leptons. For the 4 leptons, the ZZ decaying to 4 leptons, which is, it can be 4 electrons, it can be 4 muons, it can be 2 electrons or 2 muons. And this is your simulation in red for the Higgs boson in red, and this is your data in black points. And the simulation and data matches. And in fact, I will tell you something very interesting. 2011 to 2012, when we went with this data, this excess of events was growing slowly. And this was becoming very, very interesting for us to see. It was, of course, very anxious moments. But every week, every day, every week, every month, there was something being added, and this peak was coming up and up and up, and it was growing. And then finally we had this for the discovery. And then what you see here, I quote here the scientific journal called Physics Letters. This is where it was published. Why? Because see, in this type of talk, I shouldn't even talk about in which scientific journal it was published. But I'll tell you, when Peter Higgs, did this work in 1964, he first sent his work for publication in the journal Physics Letters. The editors of Physics Letters, who were based at CERN at that moment, actually rejected his paper. Sent it back and rejected it. Peter Higgs sent it to an American journal called Physical Review Letters, and it was published in Physical Review Letters. And then when it came to the discovery, when Atlas and CMS, these two huge experiments at CERN, announced discovery, we decided to send the discovery to Physics Letters, which rejected the paper of Peter Higgs, and it was published immediately. Sent, published. So this is the journal, Physics Letters P, and it's a great achievement. You see, it was a 4-decade long quest, 40 years. It was too much actually. And then a Higgs-like state was pinned down at 125 GeV mass. So finally, we could close in and observe it at 125 GeV, and this was the moment of discovery when it was announced at CERN in the huge auditorium at CERN, when these two gentlemen, I said, were meeting for the first time. And here on the top, as you can see, he was the CERN Director General at that time. He was the director of DESY, Deutsche Elektronensynchrotron in Hamburg, Rolf Feuer. Then from DESY he moved to CERN as the CERN Director General, Professor Rolf Feuer. And beside him was the CMS experiment spokesperson, Joe Incandela from Santa Barbara in the United States. And here Fabiola Gianotti, the spokesperson for the Atlas experiment, who announced the Atlas discovery at that time. She's now the Director General of CERN. So these were all the exciting moments. Joe was presenting just like me. I'm presenting like this. Joe was presenting. I was in the auditorium at that time. And here was Fabiola. And yeah, and it was really, really a great moment with lots and lots of effort of lots and lots of people. Somebody was taking the data, somebody was processing the data, somebody was reconstructing the particles, somebody was maintaining the detectors, somebody was doing the analysis. So much of effort has gone into all of this, and finally comes the discovery. So when it comes to discovery, we say it's a discovery made by the collaboration, not by an individual, because it's a joint effort of thousands of people together. It's not 20, 30 people. And it was a huge moment of joy. Got it. Like here we have. Okay, this was the. Here is a very senior professor from University of Wisconsin. She has retired. Her name is Saulan. She was the PhD student of Professor Ting from MIT, who discovered some fundamental quark in Brookhaven National Laboratory. And Saulan has retired, and she has retired long ago, but she still continues actively her research. We sometimes joke she's like the grandma, so but she's so enthusiastic. And here is one of the founding members of the CMS experiment. His name is Daniel Denegri, this guy, and he is over 80 years old now, and he's very active, very energetic. He sees me. He's one of the 5 founding members of the CMS experiment, and so there are 5 founding members. He's one of them, and he comes from the institution where I did my PhD, the Atomic Energy Commission of France. So, and he's over 80 years old. He's 82, 83 years old, and whenever he sees me, he tells me, "Oh, young man, you're still alive." He tells me this. Then last time, 3-4 years ago, I got very annoyed with him. I said, "Daniel, behave yourself. Like, is this the way? Like, you whenever you see me, you just tell me that, young man, you are still alive." He said, "Oh, you didn't understand why I say so?" I said, "No." He said, "Because attack is the best defense." Means he is he's 80, so before I tell him, he tells me. A very funny person, and from our same institution, another very senior physicist. She was the PhD student of Carl Rubia, and her thesis was discovery of the W and Z boson. And she gets extremely annoyed with Daniel sometimes. And whenever I visit CERN, we sit for coffee together, and she is always complaining about Daniel to me. Daniel told me this and Daniel told me that. It's a fun time sometimes at CERN with all the senior people who have retired long ago, but they're still actively involved. They go for meetings, they participate, and they really share ideas, they propose new ideas. They're still active. They're still active. Of course, they are playing with their grandkids at home when they go back home, but they're coming to CERN every day, and they still participate to the scientific cause. Now, we saw what? The Higgs decaying to photons, the Higgs decaying to Z boson, to bosons. But then another part is, question is, does the Higgs decay to fermions? Fermion is the spin half particle. Boson was the photons and the Z and the W, but then the quarks and the leptons, which you saw, which makes up the matter particles, they are the fermions. So does the Higgs decay to these fermion particles? And this is something we have to explore. And for a standard model like Higgs boson at 125 GeV, we should say that we are lucky to have it at 125 GeV, because if it is a standard model like Higgs boson, then you see these are the different decay products, and these are the branching fractions. So for bottom quarks or tau leptons or charm quarks, it in fact covers this 125 GeV. If it was somewhere, say here, around 300 GeV, we could not explore it, decaying to fermion, of course. But if it was above 350, then we could see it in TT bar. But this was something to explore. That does it, decay to leptons? Does it decay to quarks? So lepton is the tau, or to BB bar, or to charm bar, and we have been lucky, I would say, which I will show you in my results. But another thing, interesting thing is, you see, a Higgs cannot decay to top quarks. Why? Because the top quark mass is 173 GeV. It's more than the Higgs mass. So it cannot, but it decays to the others. And also there are some open questions that if this, by measuring the properties of this Higgs, that does the properties match with our standard model expectations, with the theory of the standard model. Also, there are different models beyond the standard model. We cannot stop here. We not only measure the properties, but we look for additional Higgs bosons beyond the standard model. And so I will not go into the details of the leptons, but I would just say that the tau lepton, which is the heaviest of the leptons, electron, muon, and the tau, means the Higgs couples the maximum among the leptons to the tau because of the highest mass. And so this tau becomes very crucial particle then, and the tau itself decays to electrons, muons, or quarks, and the quarks form hadrons. So the reconstruction of the tau leptons are extremely crucial in this challenging hadron environment, in this hadron-hadron collisions. And then the Higgs decays to tau lepton pairs, and this is the pie chart of the different decay modes of the one tau decaying to muon and the other decaying to quarks, so basically to hadrons. Say both decays to hadrons, or one decays to electron, the other decays to hadron, and so on. This is the pie chart, and here again the invariant mass spectrum of the tau lepton pairs, we find a slight excess of events here, and this is how we strongly affirm the Higgs fermion coupling and the evidence of the Higgs boson decaying to leptons. And this is an event display of Higgs going to tau leptons. So here you can see a Higgs decaying to a muon. So basically the tau decays to a muon, and here to hadrons. This is giving a problem. Yeah. So muon and hadron. This first thing which I wrote here. So this is the muon in red, and this is the hadron. So So, and then it was again with this bottom quark, it was established a strong evidence of the Higgs decaying to fermions, and this is now firmly established that the Higgs decays to BB bar, and where you can see these B jets coming out from the Higgs decay. It was reconstructed, but this is an extremely challenging analysis, as I said, because the bottom quark forms hadrons again in this huge hadronic environment, and we had to use advanced machine learning techniques. So this is something like, you know, the most cutting edge of analysis. Machine learning is used not only for us, but everywhere now, everywhere. It has lots and lots of applications, not only in particle physics, but everywhere. So we use these advanced machine learning techniques to perform this analysis and you know, discover the last of the you know, Higgs decays to bottom quarks, which I mentioned because this was the most challenging one. And then we also discovered in the production mechanism with the lowest, you know, the production rate, that was to top quark fusion, right, in association with top quarks. And this was it, like TT bar, and this Higgs was being formed from the fusion of the top quarks. So, and say the Higgs going to say tau leptons, each of the tau lepton, one goes to electron, another goes to hadrons, and then that top quark also decays to bottom and W, and then the bottom decays to further quarks. The bottom decays goes into jet, and then the W decays to jets or hadrons, and another W goes to muons, because the W boson can decay to a lepton and a neutrino, or to quarks basically, and the quarks form hadrons or jets. And this is what you could see, jets of hadrons here, jets of hadrons. This is from the W, and then hadronic tau lepton, and then the two bottom quarks here, and the muon or electron, whichever comes out from this tau lepton. So this announcement, the discovery of the Higgs boson, was done at 125 GeV in 2012. Since then we have accumulated a lot of data, what is going on at this moment, understanding the properties of the Higgs boson, but we just don't stop there. Our question is that are there additional more Higgs bosons? This is something we have to search, and because the standard model is not complete and we need to, you know, go into some physics beyond the standard model. So we call run 1 till 2012. From 2015 to 18, the data we collected is called run 2, the second regime. And because you see, at the Large Hadron Collider, we collect data for a certain amount of time, then the collider shuts down for say, a couple of years for maintenance and for upgrades, and then it restarts again. It runs for a few years again, and then it stops again. Right now the accelerator is not working, it has stopped for maintenance and upgrades, and then it will restart again in 2021. That will be called run 3. And so basically in run 1 we covered a large range of exploring different signatures. Then but I would like to stress here that the Large Hadron Collider is the discovery machine. We don't stop with one discovery, and the adventure in this TeV regime has just begun, and there's lots and lots of more data to come, and lots of more collision data to be analyzed, and further discoveries to be made with run 2 and run 3 before we move to a higher luminosity or higher rate of collision regime beyond 2025. And this collider is going to run till 2039 for 20 more years. So are you teachers from the high school, or are you students? Are you students? So from colleges? Okay, very good. So I think you plus you can tell your friends that this is not only something interesting physics, but this is something which will run for the next 20 years for you to explore. So you finish college now, you go to masters, you finish masters, you can enter PhD for this kind of exploring this kind of physics, and you can do a PhD, you can do a postdoc, you can be a scientist, but it will still keep running and running and running. And once in 2039, 2040, it stops. Once it stops in 2039 means it doesn't stop. It takes another 5, 6, 7 years to finish all the analysis of the collision data, and then there will be another collider coming, which I'll tell you at the end of my slide. And so this is a never-ending game. And then there are, as I said, different models beyond the standard model, and we are exploring everything. But so far, we have not found any further discoveries beyond 125 GeV. But as I said, see, this is something beyond the standard model. What is the standard model? You have a fourth leg here, right? Fourth tire. But this is beyond. Means you just pull out and you put something else. You put something in addition. So what you do is, you have the standard model here, but then you add something more. So these are additional things that will go into the future. So, and there are really exciting times ahead of us. And right now, there are also different detectors, different technologies, under construction and being explored, because once we increase also our rate of collisions, the present detector technology, the present, electronics, nothing will work. So basically, we need to upgrade and go into, detector technology and electronics technology, everything like, which can handle and which can read out our data efficiently without any loss. So this is the full program which I showed you. It goes 2039 on everything. And so it will be upgraded, and there will be, and you can see LS is long shut down. So this is what I was mentioning. It was shut down for 2 years after the discovery. Right now it's a shutdown phase. It's called LS2. It will start, and then there will be LS3, LS4, and LS5. There will be different shutdown phases. So prospects at CERN. So students are very welcome to join this exciting research area at this interesting regime towards discovery physics, I'd say. The Large Hadron Collider is to continue at least 2035. Actually, it's now the European strategy of particle physics says 2039. Even beyond that, this was the original, to extract the full potential of this collider, because it's very expensive. You don't build a collider every 10 years. It's really like I am a person who would see a collider once in my lifetime. It's something like that. Like I will be working on a collider once in my lifetime, because when the next collider comes, already like before the Large Hadron Collider, when the Large Hadron Collider stops, I am retiring. So you can just imagine, like when the next collider comes, I might not be alive. So that might be the thing actually. So that's the reality. So life is challenging and rewarding at CERN. It's extremely rewarding, but it's extremely challenging. Why challenging? Because the physics that you are doing, it's not something very simple and easy physics, or the technology is not something very simple and straightforward. It's complicated, but it's very interesting. You have to put in a lot of brain and lot of effort. And the best minds come from all the countries at CERN together. It's an amalgamation from all countries, the best minds at CERN. But it's extremely rewarding. You do good work, you're extremely well rewarded. So one works among the best minds in particle physics in the world, in the best settings one can imagine. Really the best settings. First of all, you go there, and I think right now, if you are in the habit of watching one movie per week, you will not even imagine about watching anything there. You just go there, you feel that environment, and you just want to be absorbed in that environment, and you just want to produce something. You take things up as a challenge, and you just want to go ahead with that. So, and that's the environment and the setting really you would want for students to be to succeed in your scientific career. Science is not easy. Science is challenging overall. You do anything, like if you want to do good physics, good chemistry, good biology, good mathematics, everything is challenging. Science overall is challenging. So lots of scope for Indian students, scientists, engineers. There's also a lot of scope for engineers and the Indian industries as well, but there's no industry people here to participate and contribute in one of the most exciting times ever. And so the search for new physics at this LHC discovery era has just begun, and also developing new generation of detectors and technology. And one thing I would like to say, this detector technology or different kinds of technologies which are developed at CERN, they're used across all fields outside particle physics. They're used for space missions, medical science, so many applications. So many applications. Like you can use for cancer therapy, for this, for that, for different. So say a detector, which you are that calorimeter, which you are building for the CMS experiment, the same detector technology we can now use with some modifications, of course, for say a space science experiment. When ISRO is launching something, we can just place it there and send it to moon or Mars or space. So it's really something which cuts across several fields of science. And then this is my last slide, which I wanted to tell you. This is called FCC, Future Circular Collider. It goes beyond 2035-40. And this is also a proposed CERN project. It is a proposed project. It has not yet been sanctioned yet. And it is a 100 TeV proton-proton collider. So it's an ultra-large, hadron collider. But you cannot do it in that same tunnel. And with even advanced magnet technology, you will still need to dig a bigger tunnel, and this is also extremely expensive. And it has to go below the Lake Geneva. It has to go below the Jura mountains, the mountains which are there. It will be a huge long tunnel. Now, by the way, another thing, do you know why we are placing this beam pipe which we have? Why is it under the ground? No, because see, when the proton is circulating, it's not giving off any radiation, like harmful radiation. To what space? Exactly. Land is expensive. You go underground. There's nothing beyond that. Land is very expensive, and especially land in Switzerland. Switzerland is a very expensive place. We said like even breathing is expensive in Switzerland. Right? So that's the right thing actually. Because see, when you are colliding the particle, everything can be above the ground. When you are colliding, if you say radiation, go at that point underground. Why the rest of the thing is underground? Just to reduce the space. So this is ultra large, and it will go around 80 to 100 kilometer tunnel encompassing all of the Geneva area and under the mountains and everything. But there are also other proposed, colliders in Japan, in China, everywhere. But most likely, when there's a CERN project, it's most likely it comes out, and it will be this future circular collider. I really look forward to that. Well, I'll not see it in my lifetime, but at least I can participate in students towards developing the technologies for the detector. When it comes, it comes. Like, I will not be there, but at least till 2035, 39, till I retire, I can just, develop those kind of things. And then this is how inside CERN, some of the lawns, some the mountains you can see, and this is Mont Blanc. Mont means mountain, Blanc is white mountain. So BLANC. This is actually where the aircraft of Professor Homi Bhabha had crashed in the 60s, early 60s. Air India flight 101, which was going to New York via Geneva, it crashed. Normally when an aircraft crashes, you discontinue that number of that aircraft. But AI 101 still operates with that number to New York Kennedy Airport. So it has not discontinued that particular number, because but it's the norm that whenever there is a crash, you discontinue that number, but you make a new number. But 101 still continues, and I travel 101 from New York Kennedy to Delhi. And so this is the site from CERN, Mont Blanc. You can see this white thing, very nice. And this is, so CERN has lots and lots of offices and buildings, and this is building 40, which houses lots of collaborators from the Atlas and CMS collaboration. This is the Atlas side, this is the CMS side, and this is where all the discovery for that Higgs boson, all the analysis have gone into. All the minds were sitting in this building. All those big minds were sitting in this huge building, as you can see. And most interestingly, you can see the Nataraj here. This was gifted to CERN by the Department of Atomic Energy from India. And this is something beyond your work. So, you know, sailing, rafting, having nice dinner in Chamonix, which is one of the hill stations, but very expensive. You go for such a dinner, you shell out your whole salary. An Indian salary is nothing compared to usually. And then you could go for hiking, for what do you say, this skiing and all this. I can't ski, by the way. I've never skied. I'm very afraid to do all those things. But people go for special, so there's a special conference in winter. It's in a ski resort. People go there and people give talks, and then people ski. So yeah, so high energy experiment is, that's why it's very not only interesting on the work front, but also, you know, there are lots of conferences where it's very interesting locations, and you can go and you know, for a week you give your talk or you listen to talks. Of course you do the physics first, and then there will be 1 or 2 days to enjoy the place as well, for a nice vacation. So that's something you can get to see a new place. So yeah, that's it. Why do you care about the relative velocity here?
This is just to understand if this is the highest possible velocity at which collisions can occur anywhere in the universe. So is that?
Yes, of course, because this is the highest energy that you are reaching to. Mm-hmm. This is the highest momentum that you are reaching to. You cannot reach beyond this anywhere. The previous one was the Tevatron.
I actually have a couple of questions.
Yeah, go ahead. See, do not hesitate to ask questions. I mean, the main point of science is, see, whenever I ask a question sometimes, I might not understand, and I say, okay, I am asking as a layman. Nobody comes as an expert. So even if it's a layman question, go ahead. This is how you develop your understanding slowly.
These particles collide 4 times in that ring. So do they lose out energy once they collide once?
Yes, of course, no. First of all, when the you know, these protons are accelerated and they go around, they lose certain fraction of the energy. So what happens is, these bunches are then flushed out, and fresh bunches of protons are injected. It all starts, the story starts from a small bottle of hydrogen. It comes out, the electrons are ripped apart. You are left with the proton. It starts with a linear accelerator. It accelerates, enters a loop, where it's further accelerated, enters a bigger loop, further accelerated, enters a bigger loop further, and then enters the big ring. And then when it loses energy, it comes out, and there is injection coming out, injection coming out. And here it's very important to note that you see we are colliding. No, collision will take place simultaneously, because it is in two beam pipes, two different beam lines circulating opposite to each other, and they meet at certain point, and that is where the detector has been kept, Atlas or CMS. Yes, yes. So of course, this is what I said, like 100 billion minus 30. So only 30 are colliding with each other, and 100 billion minus 30 says hello to each other and just pass by. And one thing interestingly, I would say that one of these experiments called LHCb, it's not actually a collision of the two proton beams. It's a fixed target experiment. So there is a target and a proton beam just goes. But this is just off the track. But we are concerned here more on the CMS and Atlas and the Higgs boson. So here, yes. And what I was coming to is that when you see there's something called synchrotron radiation. So means when this particle circulates, this high energy particle, it loses energy, and this is proportional to 1 over the mass of that particle with the 4th power. And so if it's an electron, which if we had done it here, it would rapidly lose all its energy via the synchrotron. So we don't put an electron, and instead we use a proton, because the mass is more, so the radiation loss is much less.
From a layman perspective,
Yeah.
there is still around everywhere or only on the particle?
No, no. The Higgs field, the Higgs field invades the whole of the universe.
So the mass we have
Yeah.
also because of the Higgs field.
Yes, exactly. So because what are we built up? We are built up of protons. Now, and there are electrons around. Now that electron, basically the molecule, then the atom, and so the electron, everything. So basically,
So
it
we are
invades the whole.
swimming in the Higgs field. Right?
Yes, it invades all of the universe.
And we have the gravity field.
Yeah, but gravity
It's
is
outside this standard.
yes, it's outside. It's something that cannot be tested within the standard model.
So we have a gravity field and a Higgs field full, like
Yes.
right now.
Yeah. So gravity is something like, but the Higgs field, this field invades all of the universe, and the interaction of, so for example, a photon just sees transparent the Higgs field, no mass. Electron, little bit it wants to quarrel with the Higgs field. Okay, the top quark wants to fight with the Higgs field. Okay, so the maximum mass. So that's how it goes.
So when we are detecting the boson, we know that we cannot detect it directly, so we are looking at the constituents into which it is
Because
decaying.
the lifetime is very small.
Yeah.
So before you even can capture in the detector, it decays to this part, the constituent particle, not constituent particle. This is something wrong.
Okay.
Decay particles. Because
Decay
it's not a constituent of anything. It's a fundamental particle.
True,
So
true.
it's not composed of anything.
Yeah.
Yeah.
Right.
So yeah.
Is there no probability of these particles coming from anywhere else, like apart from this collision? So
Yes,
if
yes,
we
yes,
see a-
yes. So this is your background, right? So we have our. So her question is like, say the Higgs decaying to 2 photons. Now, can't those 2 photons come from somewhere else than the Higgs boson? Yes, and this is what I was showing here. Or for example, the tau lepton. Just let me say here, the tau lepton. So the tau lepton can decay. So the Z boson can decay to tau lepton. Tau tau. So this process is coming from this. So we reconstruct this process. So this is your background or your noise, because your signal is the Higgs boson, this red thing, this small tiny artifact, and this comes as an excess here above. Same for the photon, you see. I'll just show you the photon. So these diphotons can come from a range of other processes. But this is then from the Higgs boson. But this is the reason why I first mentioned that before we go searching for the Higgs boson or any new particle, we have to have our finest of understanding, first of the detector, then of the reconstruction of particles, then the identification and performance of that particles. For example, the photons here, and then our known set of standard model particles which we have discovered so far, which can go to 2 photons, which constitute as the background or the noise. And then over and above this background, anything excess you observe, that is your Higgs boson. So what happened was, initially when you had less data, this line, what you saw here, was flat like this, like this. But then with more and more of statistics or data accumulating, this part started growing. Also these started growing, but this started growing. And this was over and above my background or my known 2 photon processes, which was not predicted, which is something new I am seeing. That's the Higgs boson.
And is there any way to know which, there are so many particles, like you mentioned, there are so many billions of particles that are colliding. So is there any way to identify that this particular particle has caused this? And is there any way that...
Billions of particles are not colliding. Billions, only
30.
30.
Yes, sorry.
But then your millions of, these particles are coming out in that splash from that collision. And so go ahead.
So when this data is collected,
Yeah.
how is it identified that what has caused these decay?
So this is something, so this is the decision level which we go into. So for example, when we are looking at an event or a collision event and say we want to look at Higgs decaying to 2 photons. So for sure we keep events which has photons in it. So which do not have photons in it, we just say okay, goodbye. What is the use of keeping those events? So like that, our interesting events, say some has muon, some has this, we keep those set of events. The rest we say goodbye, because we cannot keep everything. That's how we make the decision, based on what physics or what process or what particle we are looking for. We're done? Any questions? Please go ahead, don't hesitate, don't feel shy. Yeah. You can give her the microphone.
In one of the slide, I saw the gluon,
Yeah.
the force particle, right?
Yeah.
I saw there was a 0 mass over there
Yeah.
below. So how it collides when it has a 0 mass?
How it collides?
No, it collides because you in one of the another slide I saw Hadron collides. It deals with the gluon collides. Something it's there.
Gluon fusing into
yeah.
each other, yes.
So with 0 mass, can it collide with?
Yeah, because have you heard about 4 momenta? No, not yet. Okay, but it has an energy, right?
Okay.
It has an energy. So it has a so basically it has a momenta, right? A momenta, an energy component, because as I told you, when I just talked about the photon invariant mass spectrum, that you can say photon is 0 mass, but why do you? Because it's the energy and the angle with which you reconstruct the invariant mass. So similarly for the gluon, actually, it's your energy or the momentum. That's why you go to that higher energy, right?
Okay. Thanks.
All protons have almost equal energy and they are colliding in same.
Might not be favorable to say Atlas experiment, but might be favorable to Siemens experiment, that you have more of Higgs bosons here and less of Higgs bosons there. It's absolutely nature.
Nature means you mean there is a finite probability only, very small probability that
Yeah.
Higgs boson will be.
Yes, yes,
Okay.
of course,
Hmm.
of course. And also within that probability, there's also another probability that nature might not even produce anything there. Like
Okay.
might not even have something there.
Okay.
Whereas nature might have something for there, but not here. This is some. So basically, when Higgs discovery thing was happening, actually in the beginning, Atlas started seeing more of diphoton events than CMS, and CMS people were getting nervous. But that's actually nature.
So what is difference between there are 4 stations? One is you said fixed target, and another 3 is not fixed target. Protons are colliding.
Yeah.
So what is difference between the 3 stations then? Why not only one station?
No, no. See, there are different detectors. You want to independently say, I am tossing a coin, you are tossing a coin. I want to observe independently what is my result, you want to observe independently what is your result. You are another person, you have another way of tossing the coin, I have another way of tossing the coin.
But you are passing the same way. You are at the same angle and
No,
same
but the
energy.
detectors are different.
Detectors are same.
Yes, of course. So, the camera which we are talking about, one is a Canon camera, one is a Nikon camera.
But
So,
they are all measuring energy and momentum.
So
and,
both are
I
taking
think,
the
position.
pictures.
Okay.
Hmm?
Do you mean they are taking the error levels are different or what?
No, it's not about error level. It's about the different detector technology. So the particle reconstruction is different there. The particle reconstruction will be different here. The algorithms will be different there. The algorithms will be different here. The complete procedure is different there. The complete procedure is
No,
different.
but algorithms are finite. From basic physics, you have got your algorithms.
No. Algorithms are never from basic physics. Algorithms are from the detector point of view. Because when you are
No, what is different in detectors? I am not getting actually.
So suppose if your calorimeter is liquid argon calorimeter in Atlas, and if your calorimeter is a lead tungstate crystal in CMS,
After all, it is measuring energy or momentum
Yes,
with some accuracy.
no. But here there is a problem. The way you measure this is different.
Way means what?
Okay, in a public thing, I cannot talk about the different shower profiles and all this. But the way means you might have a better understanding. You will have more clear understanding if I talk about shower analysis. But when these hadrons or this photon, like so when they decay in a calorimeter, if you saw there was a broadening. It's called showering, basically. So in the calorimeter, so yeah, the spread and the showering. So for example, if a pi meson decays to 2 photons, and then there is a prompt diphoton production, and there is a Higgs boson decaying to 2 photons, that profile of that shower is different for each of these different, and is also different for different technologies which you use, and you have to characterize according to that detector, and you have to put it accordingly. You cannot just say, oh, this calorimeter, this is also an electromagnetic calorimeter, this is also an electromagnetic calorimeter. I cannot just put 1 to 1. It has a different technology, this has a different technology. So you have to have the proper algorithm and the proper reconstruction method for this, the proper algorithm and the reconstruction.
I have another question. Most of the algorithms might have been decided or made before this experiment was made, I think. No. They are ongoing their process. Hiding and going.
Because it depends on what we are observing and how, and tuned to our experimental needs.
Okay.
You should be the one asking more enthusiastic.
Actually, I think it will be a vague question.
Yeah, don't go ahead.
You said the camera.
Yeah. That's the detector, yeah.
So, like,
Well, to detect those particles, so by camera, I just said in a very colloquial level, it's really not a camera. It's a, it's like, okay, what I meant to say is that detector takes picture of that particle, means you reconstruct that particle through momentum and energy measurement, the angles.
Only Higgs boson particles are of such importance. I mean, why to invest so many things for only one Higgs boson particle?
No, we are not just we have not used this collider just for discovery of the Higgs boson. First of all, the Higgs boson was extremely important to understand our universe. First of all, but we have not used this collider just for discovering the Higgs boson, but we need to know if it existed or not. So, as I told you, our standard model is not complete. So we will be for the next 20 years with this collider exploring for newer particles and newer interactions which constitute physics beyond the standard model of particle physics. And then we unify picture of everything together. And it's not only that, we're also colliding, in addition of proton beams, we're also colliding heavy ions, lead ions. So we are trying to recreate a state of matter which is around 10 to the power of minus 12 seconds after the Big Bang, and trying to understand the state of matter at that phase of the universe. So there are different kinds of physics which we are trying to do through this experiment and through this collider. It's not just, otherwise we will not stop, right? We will not be operating into billions and billions of dollars. 2012, discovered, stopped. We didn't do that. Why? Yeah, ask me a question.
We are from life science background.
Okay.
So, do biologists have any role in CERN or such projects?
Yes, to a certain extent, because as I told you, that the kind of detector technology we are using, they have been used for medical science and basically biological applications. Like I'll give you just not just cancer therapy or tomography, but proton therapy, but also these clinical dosimeters and all these things are coming from the detectors we build and so on. And not just for the Large Hadron Collider, there are some other nuclear physicals too, and all these technologies are used. But interestingly, the World Wide Web, that is being used. So it's not just colliding particle and these things. So many areas. Are you all from life science background? Yes. All okay. So I think in a way, I think you have seen something beyond life science, but of course which gives life. Which gives life. I mean, which gives mass, but also it can be interesting for all of you, for technology development, research, for life sciences, for medical physics, this kind of medical physics. You can only shoot in medical physics. In India, there is actually scope for, you are all in your bachelor's? Yeah, so there is master's in medical physics in many places, and there something can be explored, then you can focus in medical physics. That is something you can explore.
So, this might be a lame question. Can this explain the origin of life or something like that?
Oh, that's a good question. It's not a lame question. You see, the Higgs boson basically comes from the existence of the Higgs field. And this Higgs field comes from something called the mechanism of electroweak symmetry breaking. Okay, I just use this terminology. Don't be too perturbed or afraid about this. I'll tell you now in very simple words. Science laws are not exact in nature or universe. There is a breaking of symmetry. where here there was a breaking of symmetry which gave rise to the Higgs mechanism or the Higgs boson. So science is not exactly symmetry. Why? That's why you are existing today, I am existing today. If matter and antimatter were in equal proportion, oops, none of us, chairs, tables, microphone, you, me, rivers, valleys, trees, nothing will exist. So there's an asymmetry. There's more matter. That's the existence of universe after the Big Bang, and then you have this. Vigyan College. It's in Bangalore? Okay. Okay, and you are doing your bachelor's in zoology, botany, microbiology. Okay. So actually, that's my mother. She wanted to hear a public lecture because she never heard me speak. And she told me, I want to know what the Higgs boson means. You never explained to me, and this will be in such colloquial thing. And she was a zoology student, life science. So she will be more familiar with your questions, what you asked. So she retired long ago. So now she is again back to school. So let me ask you one. Okay, can somebody tell me what is the? Did you talk about how many magnets are there? Oh, the number is okay. I didn't put that in my slide, so I will not ask you. It will be very unfair. It will be very unfair. Can somebody tell me what is the full form of CMS? You heard CMS experiment? Yes. Yes.
Ibrahim.
Ibrahim. Ibrahim what?
Ibrahim Enes.
Ibrahim Enes. So which standard are you? Sixth standard. Which school? Green Valley. I am very pleased to meet you. I am very pleased to meet you. Yeah. This is yours. Fantastic. Or do you like this? Which one do you like? Which book? Choose quickly.
I think I take this.
You take that. Okay. Okay. Okay, my next question. So this is the last question, of course, because I just have one book left. What is the maximum collision energy which the Large Hadron Collider can reach?
$13 tera electron volt.
Yes. And no, the collision energy, the maximum collision energy.
7,000 GeV.
That's 7 tera electron volt.
173 G.
No, that's the mass of the top core. And you cannot go to GeV, right? Then you don't know. No, but like that everybody. Huh?
14.
Yeah, 14 TeV. So, okay, okay. So the father and the son duo have that's great. So the son has both the books. So you didn't have to choose now. You have both the books. That's fantastic.